Recording in progress. The next example, R1 is a relation on set A, where set A is 1, 2, 3, 4 up to 15. And R1 is defined as x comma y. X comma y is an ordered pair. Okay. 3x minus y is equal to 0. 3x minus y is equal to 0. So this is the relation R1. Now we'll first find out the ordered pairs. 3x minus y is equal to 0. Therefore, y is equal to 3x. Okay. So when x is 1, the value of y is 3. When x is 2, put 2 over here. Value of y is 6. When x is 3, value of y is 9. When x is 4, value of y is 12. And when x is 5, the value of y is 15. So we got the ordered pairs. Okay, we got the ordered pairs using this particular relation between x and y. So I'll just note down the ordered pairs on the next page. R1 has 1, 3, 2, 6, 3, 9, 4, 12, 5 and 15. Now first thing is reflexive. Okay, now R1 is a relation on set A. R1 is a relation on set A. And set A has all these numbers 1 to 15. So reflexive says 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6 till 15, 15. Everything should be there in R1, but then unfortunately it is not there. So 1, 1, 2, 2 up to 15, 15 does not belong to R1. Therefore, not reflexive. Therefore, not reflexive. I hope you got the point. Then we'll start with symmetric. Even if one example fails, everything fails. Now 1, 3 belongs to R1. Just reverse this. 3, 1, does it belong to R1? No, it does not belong to R1. Therefore, it is not symmetric as well. Okay, therefore it is not symmetric as well. Fine. The third thing that we need to check is transitive. Okay, so I'm just writing it over here itself. Transitive. Okay, so let's take this ordered pair. 1, 3 belongs to R1, which is true. It's true because it is belonging to R1. Now, is there any other ordered pair which starts from 3? Yes, 3, 9. 3, 9 also belongs to R1, which is true. Both the statements are true. Now, this should imply what? 1, 9 should belong to R1. Does it belong to R1? The answer is no. The answer is no. Therefore, this is not transitive. Even if one example fails, everything else fails. Okay? Yeah, I hope you all understood this particular point. Okay, Next example. This is the next example. R1 is a relation on R1 is a relation on natural numbers, and R1 is defined as is square of is square of. That means the first number is the square of the other number. So we will check reflexive property. Okay, now natural numbers they start from 1. Now 1 is a square of 1. This is true. But then is 2 a square of 2? Is 2 a square of 2? No. 3 is not a square of 3. So even if one example fails, everything else fails. So this is not reflexive. Okay. Now we'll discuss symmetric. We'll discuss symmetric. Now 4 is a square of 2. Now this belongs to R1. This is very true and which belongs to R1. 4 is a square of 2. Just reverse this 2 comma 4. Is this true? Anyone? Is this true when we reverse it? 4 is a square of 2, but then is 2 a square of 4? Waiting for your answer. This is false because this does not belong to R1. The relation is a square of. So first number should be the square of the second number. But then when we reverse it, it's not necessarily true. Okay, so it's not symmetric. Now let's check transitivity. We'll take two examples where the squares are quite valid. And we have to take natural numbers only. 16 is the square of 4. It belongs to R1 because it's true. 4 is a square of 2, which is also true. These both statements are true. They belong to R1 because they follow this particular rule, is a square of. Now tell me guys, 16 comma 2, will it belong to R1? Will it belong to R1 or is this true? 16 comma 2 implies what? 16 is the square of 2. Is this true or false? If you please reply, it will be good for me to know. Be quick, come on. Yes, this is false. This is false. So it does not belong to R1. So it is not transitive. It is not transitive. Okay. Yeah. Next example. R1, okay, is defined as A comma B such that A and B belongs to set A and A minus B is less than 5. A minus B is less than 5. Whereas set A is real numbers. Set A is real numbers. So first I'll check whether this is reflexive or not. Whether this is reflexive or not. Now reflexive property says A relates to A. So A minus A. So instead of B, I'll just write A because A relates to A. Replace B with A. This is 0. Is 0 less than 5, guys? Is 0 less than 5? The answer is true. The answer is true. So it is reflexive. So it is reflexive. Okay, let's understand symmetric. Let's understand symmetric. Okay, let's take an example which is true. One second. 2 comma, let's say 8. 2 comma 8. This implies what? 2 minus 8. This implies 2 minus 8, which is equal to minus 3. Now minus 3 is less than 5. So this is true. Minus 6. I'm sorry, minus 6. Okay. Minus 6, which is less than 5, which is true. Okay. Now 8 comma 2. Just reverse this. 8 comma 2. Remember this example specifically, yeah? Because otherwise you'll just keep on searching. So remember this example. 8 comma 2 implies what? 8 minus 2, which is 6. Is this less than 5? No. So the reverse is not always true. So this is false. So this is not symmetric. It is not symmetric. Okay. Let's go to transitive. In transitivity, first two examples should follow the rule. First two statements should be true. Transitive or transitivity we are checking. Let's say 5 comma 1. 5 comma 1, the difference is 4, which is less than 5. So this belongs to R1. Okay. 1 comma, let's take a negative number, minus 3. This also belongs to R1 because 1 comma minus 3 implies what? 1 minus minus 3, which is 4. 4 is lesser than 5. So both the statements are true. Remember this example as well. Now 5 comma minus 3. 5 comma minus 3 implies what? 5 minus minus 3, which is equal to 8. Is this lesser than 5? No, this is not lesser than 5. So here it is false. First two statements are supposed to be true because we are checking transitivity. The implied statement A comma C should also be true, but then it is not true, it is false. Remember this example for your board exam. Otherwise, you will keep on searching. Okay, so this is not transitive. And yesterday we did one thing. If a function is reflexive, symmetric, and transitive, it is called as equivalence relation, or it has equivalence. Okay. Yeah. Next example. Again, in this particular example, you have to remember the values which I am giving you. R1 is a relation. Okay. Which has A comma B. Which has A comma B. A and B belong to real values. A and B belong to real values. A less than or equal to B cube. A less than or equal to B cube. Now reflexive. Reflexive. Now we are speaking about all real values. Don't take in only examples of natural numbers or integers. You can take example of decimal numbers also. Okay. So reflexive, every real value. Now let's take some natural values. Let's take 2. Okay. And let's take 2 cube. What is 2 cube? 8. Okay. So 2 is less than or equal to 2 cube, which is 8, which is true. This is true. Okay. Let's take 1. 1 less than or equal to b cube. B is a only over here. 1 cube, which is 1. So 1 less than or equal to 1. That is also true. Let's take 5. A is 5. B is a itself. 5 cube. 5 cube is 125. So 5 less than or equal to 125. This thing is also true. Okay. Let's take some negative values. Let's take -2 and -2 cube. So -2 and -8. -2 and -8. Is this condition true? Is this condition true for the negative values? Yes or no? No. So it is failing for negative values. Let's take fractional values 1 upon 2 and 1 upon 2 the whole cube. Remember these examples, huh? So 1 upon 2 and 1 upon 8. Is this lesser? Is this lesser in the next example? No, 1 upon 2 is 0.5. 1 upon 8 is very less than 0.5. It is not greater than 0.5. Here also it fails. So it is failing at the some negative values and fractional values also. Okay. So it's not reflexive. It should be true everywhere for every real value. Now symmetric. Again for symmetric, remember this example so that you don't have to search it or think over it separately during the time of your exam. Symmetric. Okay. A comma B. Let's take A comma B as 1 comma 2. Now the relation is 1 lesser than or equal to 2 cube. This is true. This has to be true. The first statement has to be true. But then the reverse we need to check whether it is true or not. So A is 1, B is 2, 1 lesser than or equal to 2 cube, that is true. Now let's take 2 comma 1. This is A and this is B. Okay, so 2 less than or equal to 1 cube. Is this true? Is this true? No. So it fails. So remember this particular example. Even if one example fails, the entire category fails. So it's not symmetric. Okay. The third part, transitive. Transitive. 80 comma 5. Remember this example. This belongs to R1 because 80 is less than or equal to 5 cube. 5 comma 2 belongs to R1. This is also true because 5 is less than or equal to 2 cube. Now we need to check this 80 and 2. 80 comma 2. This implies what? 80 less than or equal to 2 cube. Is this true? Is this true? The answer is no. This is false. So you have to give at least one example which fails if it is failing. Okay. So it's not transitive. Fine. So for this problem and the previous problem, you just remember the examples. Otherwise, You'll have to keep searching and thinking over it again and again. Yeah. Now the same problem you can do or practice for a less than or equal to b cube, b square, sorry, not cube, square. So this you practice it at home by taking some examples, a less than or equal to b square, and try to find out whether it is reflexive, symmetric, and transitive. And try to find out whether it is reflexive, symmetric, and transitive. Okay? Yeah. Next, R1. It's a relation on natural numbers, and R1 is defined as is a factor of is a factor of. Okay, this is the question. R1 is a relation defined on natural numbers, and R1 is further defined as first number is a factor of the second number. So reflexive natural numbers. 1 is a factor of 1. Is this true? Yes. 2 is a factor of 2. Yes. 3 is a factor of 3. Yes. 4 is a factor of 4. Yes. So it is reflexive. Every number, every natural number is related to itself. It is related to itself. Let us go ahead with symmetric. Symmetric. Now 4 is a factor of 2. This belongs to R1 because it's true. 4 is a factor of 2. Now reverse this 2 comma 4. Will it belong to R1? Is it true or false after reversing the statement? After reversing the statement, it is false. 2 is not a factor of 4. Okay? Does not belong to R1. One second, I just made a small mistake conceptual. Let me just think over it. Uh, I guess I took the wrong example in the first part. Sorry for that. 2 is a factor of 4. This belongs to R1 because this is true. Because 2 is a factor of 4. Because when we factorize 4, do we get 2? Yes. I considered the reverse way. Sorry for that. 2 is a factor of 4 because when we factorize 4, we do get 2. Okay. Now let us reverse this. When we because 4 is a multiple, okay? So this is not symmetric. Fine. I hope you made the changes. Then transitive. Transitive. Okay. Now first two examples should be true. 3 is a factor of 9. which is true because when we factorize 9, we get 3. So 3 is a factor of 9, it belongs to R1. 9 is a factor of 27 because if we factorize 27, we can get 9. Okay, this both are true. They have to be true to check transitivity. Now check this 3 comma 27. So is 3 a factor of 27? True or false? When we factorize 27, will we get 3? The answer is yes. So this is true. So it is transitive. It is transitive. Okay. Yeah. Next problem. I'll write the same thing, but then instead of factor, I'll just write multiple this time. Instead of factor, I'll just write multiple. First number is the multiple of the second number. So reflexive. We are discussing all natural numbers. 1 is a multiple of 1. 2 is a multiple of 2. 3 is a multiple of 3. 4 is a multiple of 4. Everything is true. So this is reflexive. Okay. Symmetric. Can you work it out for yourself? Take some examples. And even if one example fails, everything else fails. Now the first statement should be true. 18 is a multiple of 6. So 18 comma 6 belongs to R1. R1 is the relation because 18 is a multiple of 6. Now reverse this. 6 comma 18. Is 6 a multiple of 18? Is 6 a multiple of 18? No. 6 is not a multiple of 18. Okay. So it's not symmetric. We'll check transitivity. Transitivity. First two statements should be true. 81 is a multiple of 9. 9 is a multiple of 3. Okay, they both belong to R1 because both the statements are true. So now guys, is 81 a multiple of 3? Can we write like this? Does it belong to R1? True or false? It is true. It will belong to R1. So it is transitive. Okay. Next one. R1 is a relation on set A 1, 2, 3. And R1 is 1, 1, 2, 2, 3, 3. There are only 3 ordered pairs. So reflexive. Yes, it is reflexive because 1, 1, 2, 2, 3, 3, everything is there. Symmetric. Now, when I say 1, 1, the reverse is also there in the relation. 1, 1, just reverse it. It's 1, 1 itself. It's there in the relation. 2, 2, reverse it. It's there in the relation. 3, 3, reverse it. It's there in the relation. So it is symmetric. So it is symmetric. Transitive. If you remember yesterday's discussion, you will be able to answer. Is it transitive? The thing is, we cannot really check for transitivity over here. Because when I say 1, 1, the other link should start with 1. The other link should start with 1 and some other number. So we cannot really check any transitivity over here. Okay? And there is no other ordered pair. There is no other ordered pair starting with 1. So that we can combine 1 and this last thing and prove it is transitive or not. So we cannot really check transitivity over here. And whenever we are not able to check transitivity, it is transitive. So this is equivalence relation. This is equivalence relation. Okay. Next example. Less than or equal to. Less than or equal to. So reflexivity we are checking. A. Is A less than or equal to itself? It should be either less than or equal to. So is it less than or equal to itself? The answer is yes. So it is reflexive. Symmetric. Okay. A comma B. So let's say 2 less than or equal to 3. 2 is less than or equal to 3. This is true. This has to be true to check it being symmetric. Reverse this. 3 less than or equal to true. 3 less than or equal to 2. Is it true? Is this true? False. So 2 comma 3 belongs to R1, but 3 comma 2 does not belong to R1. So this is not symmetric. This is not symmetric. Transitive. Let's say 10 less than or equal to 2. This is true. So 10 comma 2 belongs to R1. Let's take a bigger number, sorry. Let's take 7. Oh, I'm really sorry. I'm really sorry. I just messed up this. It's not really great. Lesser than, sorry. Brain fade. Uh, 4 less than or equal to 7. This is true. 4 less than or equal to 7. This is true. 7 less than or equal to, let's say 9. This is true. 7 less than or equal to 9. This is true. Both the statements have to be true to check transitivity. Now let's check this. 4 and 9. Is this true? Is this true? Waiting for your answer. So this is also true. So in this case, this is transitive. This is transitive. Okay. Let's proceed. R1 is a relation on natural numbers, all natural values. R1 will have ordered pairs. A comma B relates to C comma D. equal to implies AD equal to BC. Product of the extremes equal to product of the means. AD equal to BC. Okay. So now let's check whether this is reflexive or not. Now A comma B relates to A comma B with itself. In reflexivity, we check the object or the ordered pair with itself. As per this logic, product of the extremes is equal to product of the means. Is this mathematically true? Because A and B are natural numbers. 3 into 8 is equal to 8 into 3. Is this true? Yes. Therefore, it is reflexive. Okay. Now symmetric. A comma B relates to C comma D implies AD is equal to BC. This is true because it is given. Now let's check the reverse part of it. CD relates to AB. This implies product of the extremes C into B is equal to product of the means D into A. Are these two equations same? AD equal to BC, does it imply CB is equal to DA? Is this true? Yes or no, guys? Waiting for your answer. Yes, it's true. Therefore, it is symmetric. Now we'll check transitivity. AB relates to CD implies AD equal to BC. It's given. CD relates to EF. This implies, by the given logic, it implies CF is equal to DE. Equation 1, equation 2, these two statements are true. Okay. Now we need to prove whether the first ordered pair is related to the third ordered pair. Okay. So what we'll do, we'll multiply 1 and 2. So AD, CF, BC, DE. AD, CF, BC, DE. So CD is getting cancelled. So this gives me AF is equal to BE. The meaning of this is A comma B relates to E comma F. Why like this? Product of the extremes is equal to product of the means. That's why this is also true. So this implies this. So it is transitive. And since this is all three, reflexive, symmetric, and transitive, it is an equivalence relation. An equivalence relation. Okay. Yeah. Now one last example, then this topic will get over. Okay, so R1 is a relation on a set of natural numbers. On a set of natural numbers, it is defined as A comma B relates to C comma D equal to implies product of the extremes into sum of the means equal to product of the means into sum of the extremes. First, it is product of the extremes into sum of the means equal to product of the means into sum of the extremes. Okay. So reflexive. A comma B, does it relate to itself? That we need to check. This implies what? Product of the extremes into sum of the means equal to product of the means into sum of the extremes. Is this statement mathematically true? A, B are natural numbers. Is this statement mathematically true? Yes or no? So this is right. Therefore, it is symmetric. Reflexive, sorry. Therefore, it is reflexive. Second, symmetric. AB relates to CD implies ADB plus C, BC A plus D. This is true as per the given condition. Now let us check the reverse. This also has to be true. So product of the extremes, sum of the means equal to product of the means, sum of the extremes. So is this true? Is the reverse also the same thing? Are both statements same? Yes or no? Okay. So it is symmetric. It is symmetric. Now we need to check the transitivity as well. We'll check the transitivity. So transitive AB relates to CD implies ADB plus C, BCA plus D. Equation 1. CD relates to EF implies CF D plus E equal to DE C plus F. Equation number 2. Fine. Now we'll have to follow a different approach for this problem. Remember this, by heart this particular solution and go for transitive. Okay. Now see, from 1, what does 1 say? ADB plus C is equal to BCA plus D. ADB plus C, BC A plus D. Cross multiply, take AD terms together and BC terms together. Or rather do one thing, sorry. Keep the plus sign in the numerator, okay? Always keep the plus sign in the numerator in this problem. B plus C upon BC, A plus D upon AD, split B upon BC, that is 1 upon C, plus C upon BC, 1 upon B. A upon AD, 1 upon D, D upon AD, 1 upon A. Let this be equation number 3. Let this be equation number 3. From 2, CF D plus E, CF D plus E equal to DE C plus F. Keep the plus sign in the numerator and group the terms, like terms. Split DE upon DE is 1 upon E, E upon DE is 1 upon D. C upon CF is 1 upon F, plus F upon CF is 1 upon C. Equation number 4. Equation number 4. Add 3 and 4. Add 3 and 4, left hand side, right hand side, right hand side. So 3 plus 4 we are going to do. Okay. So 1 upon C plus 1 upon B plus 1 upon E plus 1 upon D equal to 1 upon D plus 1 upon A plus 1 upon F plus 1 upon C. So 1 upon C, 1 upon D gets cancelled. Take LCM, B plus C upon BE, A plus F upon AF. Solve this. A plus F or F plus A, both are correct. So AF, B plus E, BE, A plus F. Again I cross multiplied. Now this implies AB relates to EF. How? Product of extremes into sum of the means equal to product of the means into sum of the extremes. So we got this. First ordered pair is related to the third ordered pair. Therefore, this is transitive. Therefore, this is transitive. Okay. So I have tried to cover many examples here in the last 2 sessions. The chapter is very short and we have completed relations over here. Okay. Thank you.